voltage signal, and we can get high voltage from that device. That is called amplifiers. So this device can perform operations, mathematical, as I mentioned, as well as it can perform amplification out of the signal. So operational amplifier, in short, also called as op-amp. Op-amps. You can see this one. In short, op-amps, we call that one. So this is the schematic symbol of operational amplifier, girls. Operational amplifier consists of two inputs and one output. Okay, it comes in IC, basically. You can see this is the IC. I think if I am not forgetting or remaining, it is 741 IC. The number of this IC is 741. Not 0, LS741, I believe, or maybe 01. So this IC is basically 8-pin IC. Here you can see pin numbers. So how would we know from where we should start the numbering of these pins? So for that, this is a diode here, or sometimes there is, a dot here you can see. So that implies that basically we need to start counting the numbers from 1, 2, 3, 4, 5, 6, 7, 8. So here pin numbers are also mentioned. Pin number 2 is basically inverting input. What is that one? Whatever I give here as an input, if I give input here, I will be getting output as a inverted form. Yani, if this is a signal which I am applying here, I will be getting here amplified, but it will be inverted. Can you see these two signal difference? The difference, first amplification, yani voltage level is high. Another thing is there is a phase shift of 180. You can see here it is starting with the positive cycle, but here it is starting with the negative cycle. Means yani there is a phase shift, 180 phase shift. That's why we called inverting terminal. Inverting, yani it is inverting the phase shift. Also, for example, if I apply the level, voltage level, for example, +2. So here I will be getting amplified output, but that will be minus because of inverted. Now we will be not getting -2 actually, because amplification is also there, right? So amplification, yani a factor which will multiply this input, then we will be getting more output. So one factor is also there, right? That will be there. That's why I'm not writing here 2, because it may be 10 or something, depend upon the amplification factor actually. We'll discuss now later on. So this is something. So pin number 6 is the output, and V positive, V negative, these are basically called, to set the out, what you call offset basically. So we can set sometime because, the operational amplifier gain is very, very high. So sometime it happens even after we are not applying any input, we can get some output. So in order to make it nullify, make it null, when there is no input, we should not get any output. So we need to use these voltage levels actually. That's why it is there. So it is pin number 4 and 7. So now you can see pin number 2 is inverting. Pin number 3 is non-inverting. Yani if I apply here 2 volt, girls, so I will be here getting positive because it is non-inverting. Yani there will be no phase shift. Yani for example, if I apply this way signal, so I will be getting amplified as well as in the same phase because of it is non-inverting. That's why. Okay, this is the reason. All right. So this is power connection. This is NC, girls. NC yani not connected. It is not in use. V positive, V negative, output, balance. So these are the pin numbers here mentioned. All right. Now, this is op-amps without feedback. First of all, you need to understand what is feedback. Girls, I am teaching to you something and I am asking you a question. Okay, is it clear or not clear? So when you say teacher not clear, so I need to repeat it. So what basically the feedback is, the output is I am teaching you something and based and you people are giving me feedback. So here is the output, girls. If I connect some portion of the output via a resistance to the input, it is called feedback. Getting point? Or what we can say, closed loop. Yani we are closing the loop here. This is called feedback. So we will discuss 2 configuration. One is feedback and one is without feedback. One which is there in the picture is without feedback. As you can see, there is no output connected to the input. So we call this one open loop configuration because there is no loop, right? So open loop configuration, or we call without feedback configuration. All right. Now see, so here is a formula to get the output, girls. The formula is V out, and this is the gain. I told you it will amplify the signal. So gain is a factor which is gonna be multiplied with the difference voltage which we are applying here, girls. So the formula is gain multiplied by V plus minus V negative. So depending upon which one is more, which one is less, the output will be there. So let's see. V positive is greater than the V negative. So you can see this factor will be positive. Positive multiplied by the gain, the output will be positive. Now, for next case, for example, V negative is larger. If it is not larger, girls, so this difference will be negative, and we will multiply the gain, and we will be getting negative output. All right. So this is op-amp without feedback, girls. So here is one issue with the without feedback configuration, which is that the gain of the operation amplifier without feedback is so high that we cannot control it. Yani we cannot use it as a practical purpose. That's why it is useless. Yani this configuration is useless for us. You can see now here, note a gain of 200,000. Can you imagine? It's too much. Okay, makes this device here illustrated here practically useless. Yani we have a circuit here, 5 volt or 3 volts are required, and if I use this device, so it will give me 2000 volts, 200,000 volts, which is it's gonna be useless for me. Okay, so that's why we did not use this open loop configuration or without feedback. We will be using feedback configuration. So next I will be telling you what is feedback configuration. But before that, there is some ideal and practical consideration of the operation amplifiers. Let's see first that. Okay, so did you read it, girls? So, these difference usually asked as a question, what are the practical consideration? See, so practically we call that the voltage gain, yani the gain I just mentioned to you is high. But ideal configuration, we said that it is infinite. Infinite yani very high. So ideally we say, okay, voltage gain of an operation amplifier is infinite. But practically it we call high. Another thing is input resistance. You see here, we are connecting here input. This is the input resistance. So this resistance is basically used to be very high so that both the inputs, inverting and non-inverting, can be separated and applied to the device. So it is usually very high so that it will behave like a no current will flow here. But ideally we call that one it is infinite. And girls, do you know when the resistance is infinite, can current pass through it? If resistance is infinite, yani is very high, so can current pass through it if it is infinite? No. So can I say it is an open circuit? Yani if current cannot pass in an open circuit, right? So this is something. So ideally we call that it have infinite input resistance, yani input resistance is open. This is the configuration. Okay. Another thing, we have also output resistance, girls. So output resistance here is low output resistance. Okay. Practically we call it is low. But ideally low word is replaced by the zero. Yani zero means, girls, remember the short circuit, right? Zero resistance, yani short circuit, yani all current can pass through it. It is like short circuit. And this is the symbol. So you can just memorize just these things. Ideal infinite voltage gain, ideal infinite input resistance, and zero output resistance. Practically, you will use the word high, and low. That's it. So this may ask you a multiple choice question or something there. So you can just memorize this one. So it's important. All right. Next. So now I am going to explain to you feedback configuration. So this is the feedback configuration, girls, as you can see, because the output is connected to the input via this resistance R2. It is called inverting amplifier. Inverting. Why inverting, girls? Because I am applying input to the inverting terminal and non-inverting terminal is connected to the ground. And do you know how much voltage if I connect to ground? Will it be 0 volt or not? When it is a ground, we know that one, right? All right. Okay, now listen here. So girls, here is a point. Okay, what is that? That we call virtual ground. Please focus here. What is a virtual ground concept? It says that, girls, whatever is the voltage to this point, it is gonna be same to this point. Again, I am repeating, whatever voltage to this point, it is gonna be same to this point. Because I am connecting this point to the ground, yani 0 volt, so voltage here will also be 0. Getting point? So now we are going to say that this is the current which is passing from output to input, like this. Or even I can say, anyways, if current is coming here, definitely our current will go there, because no current will go here, no resistance, and it is, ideally open. So like if I say this is I2 current, girls, let's suppose this is I1 current. Okay. And if I apply here KCL, and let's suppose at this point, the voltage is, we know that one voltage is how much. Okay. So I'm not writing this one, just I'm writing 0 volt. So can I apply KCL to this point, girls? KCL, Kirchhoff current law. And according to that, can I say I2 is equal to I1 at KCL when we apply KCL there? Is it clear? Because I2 is the incoming current and I1 is the outgoing current. We can say, this KCL. Now, girls, we need to find this I2 now. So in order to find the I2, girls, what we need to find the voltage difference between these 2 points and divide by the resistance, we can get this one. So as the current is flowing from here, so this is the higher voltage. So we will say here, V out minus 0. Why 0? Because here is the 0 voltage. Did you get the point? So from here to here, higher to lower, we are going. And this is V out minus 0 divided by R2. Same way, can you tell me for the I1, girls? I1 current is flowing from this point and going to this point. So what should I write here? 0 minus
V
in over R1.
R1.
Correct. This is the way. Okay, girls. So yes, now we can just simplify this one. So I can say V out is equal to minus R2. I am just cross multiplying over R1 multiplied by V in. Is it clear? This formula now?
Yes.
Okay. All right. Here I will assume AV, voltage gain, is equal to minus R2 over R1. And I can say V out is equal to AV into V in. Now, girls, means the output will be here V in multiplied by the voltage gain. And can you see this one? This gain is a ratio. Is a ratio of R2 and R1. And what is the minus sign signifies here, girls? Minus sign is telling that I am applying input to the inverting terminal, which is here. That's why my output is negative. Correct. Now, girls, by varying the value of R2 and R1, can I vary the gain here? Can I control the gain here? Because AV is equal to R2 over R1. So if I change the value of the resistance, can I change the gain also? Can I control the gain also?
Yes, we can.
We can, right? So this is the concept here. That's why feedback amplifier is more useful, because we have a control over there. We can control the gain over there by changing the value of these two resistances. So this is the basically the equation which you need to remember, memorize. So it is here, they are writing They are also telling it is inverting amplifier because the minus sign we are getting negative sign here at the output. This one, okay, which I explained to you. So you need to remember this equation and what is the gain. This is called AV, yani voltage gain. Okay, I can show you in the fall stat also. Just give me a minute. Fall stat, okay. So Chrome. Okay, see here, op-amps, amplifiers, inverting amplifier, seagulls. So here we are applying AC. The good thing is operation amplifier can work AC as well as DC, no problem at all. So if you want to use DC, you can just bring here what you need, like input sources. So we can have DC sources. We can connect this one. Okay, you see this one. I can change 5 volt is there, and you can see the output also. You want to see the output. Okay, this is input, and output is here. New scope. So this is something. Okay, this is the current, and let's just let me check. Undo. Okay, let's just see this one first, because there will be confusion otherwise. So see girls, how much voltage I am applying. You can see 5 volt AC. Okay, and you can see how much voltage I am getting here. Can you see maximum? 14.99. Yani, how much it is? It is almost 15. So 5 volt I apply here, max I am getting here 15. So here I will show you one more thing, like as I told you, what it's about the inverting amplifier. So look here we are getting negative, but see what is the output at that time. Is this positive or not? We are applying this negative cycle and we are getting positive. It is yani 180 phase shift is there. Amplification you can check. I apply 5 volt maximum. I am getting 15 volt here. So now, do you remember the formula? What was that? V out is equal to minus R2 over R1 multiplied by V in. So girls, check what is R2 minus R1, yani gain. So R2 value is 3 over 1, yani 3, gain is the 3. So minus 3 multiplied by 5, you will be getting minus 15. So gain is yani 3 is the gain. So 3 times I will be getting the output. Did you get the point?
Doctor,
Yes.
how to know which R is R2 and R1?
Okay, this one is the R2. This one is the R2. Always, because feedback resistance. This is feedback resistance and this is input resistance. Because we are giving from here to here. So in the formula, this is R2 actually, or sometime we call RF, feedback resistance. Clear?
Yes, thank you.
Okay, yeah, this is the one. All right, so this is inverting amplifier, girls. Okay, so it is inverting the input and it is also amplifying the signal. This is something. Now, girls, another one is non-inverting. So in non-inverting, what is gonna be there? I'll explain first, then I will be back here. So let's see this one. So this is inverting. Another one is non-inverting. So non-inverting, girls, input will be given to this non-inverting terminal, and inverting terminal is gonna be connected to ground. Keep in mind, R2 and RF will R1 and R2 will be here only. This is the connectivity, the way how can we connect, because the gain we will be getting from then this way only. So now I will try to explain you how can we get the equation for the output. So as I mentioned to you, virtual ground concept, girls. So can you tell me again how much voltage is there to the upper this black red dot?
Zero voltage.
Zero voltage. Why zero voltage? Why it will be 0? What virtual ground concept says? It says it will be 0 always. Is it like that?
Because it's connected to the ground, and the ground is always 0 voltage.
What is connected to ground? I told you how much, whatever voltage is here, same voltage will be here. That is what we call virtual ground concept. So what we are connecting here? V in. So here we will be getting V in. Did you get, all of you? Did I say same thing or not? Earlier we were connecting here ground, so same voltage was there 0. But now we are connecting V in, so same V in will be here. Clear to all? Right? Now apply the again KCL. So let's suppose it is I2, as I said earlier, and this is I1. So when I apply KCL at this dot, so see what will happen. So it is gonna be I2 is equal to I1, and what I can write for I2? V out minus V in over R2 is equal to V in minus 0 over R1. Correct? Clear to all of you? Okay, now just rearrange. So can we cross multiply this R2? So if I cross multiply, I can write V out is equal to what? R2 over R1 V in, because this is 0, so it will ignore bus here. So this is some, no, sorry. And this V in will also go there now. Clear? Check it first.
Yes.
Right?
Yeah.
Okay. So now, can we take something common, right side?
Yes, Vn.
V in is the common, right? So when we take V in, you know what we will be getting? 1 plus R2 over R1 V in. This is the output equation of this configuration, which I can say V out is equal to AV V in. And what is voltage gain, girls? 1 plus R2 over R1. Not 1 plus R2 over R1. V in, what you are multiplying with the V in? 1 plus R2 over R1. Na? So this is the gain. Clear? Okay. So this is what we call non-inverting gain. AV 1 plus R2 over R1. But for the inverting, and see, did you get this time negative sign? No. It is because of we are connecting input to the non-inverting terminal. Clear? Okay. Now see. So I can show you also now non-inverting terminal here. So let's go here and say the non-inverting amplifier. Non-inverting amplifier. So this is non-inverting. You can see plus is up, negative is down. This feedback will always be connected same way. Keep in mind, okay? This is also connected this way, always. And now V is connected this one. So we are connecting this way. And this one is connected to ground. But anyways, we have to connect this one to ground also. So that's why it is like that. Otherwise, we can have two grounds. If you have any confusion, so we can do like this. This is ground connected, so I need to have one more, so which I connect like this. So this is also the same thing, and it is just upside down, you know, it's just flip. Now, so when I turn it on, girls, you can see now how it is working. First of all, try to look. The input and output are in the same phase. Starting positive, output positive, correct? Also, try to check it, the amplification. Amplification. Here is 5 volt and here is 15 volt. Can we check it by the formula gain? A is equal to 1 plus R2 over R1, AV, voltage gain. So what is R2? Again 2 over 1, which we can get 3, not the volt, sorry, 3 is bus 3. So this is 3. So yani it means is that 3 times we are getting the output. Girls, you wanna change the gain? If yes, so you have a point here to yani by changing the value of the resistance. For example, if I change it to 2 now, so what do you think? How much gain I will be getting? 1 plus 2 by 2, which is 1 plus 1, yani 2, correct? So I should get double of the input, right? See now. Can you see now? 10 volts. So I apply 5 volts. I am getting here 10 volts. This is something, right? So now we have control over the gain. As per requirement, I can increase the strength of the signal. So this is basically inverting and non-inverting amplifiers. Both we use in back configuration because of open loop configuration is provide us very high gain. So we did not use this one. Okay. All right. So this is all about the inverting and non-inverting amplifiers, girls. Now, next thing is the application. Yani we know that how to use operation amplifier and what are the configuration, how can we control the gain. Now, girls, the applications, it consists of lot of applications, actually, so we are just considering 2. We eliminated a lot of things from the book. So just, few things. First, summing amplifiers, yani it can sum more than one signals, yani add, correct. Or it can also perform integrations, differentiation of the signals. I will show you this one also. So look one by one. First, we'll look for the summing amplifier. So summing amplifier is this. This is the one. So configuration is fixed. We will apply to the inverting terminal, and non-inverting terminal will be connected to the ground. And you know that the virtual ground concept is gone. This point is gonna have 0 volts. So girls, here can we apply again KCL quickly? If I apply KCL, can I say IT is equal to I1 plus I2? Am I right? Incoming current is IT, right? And outgoing currents is I1 and I2. So girls, write the try to find the values of IT. So for the IT, can I say V out minus 0 over RF, feedback resistance. Now they are giving the name RF because this is R1, this is R2. So just to avoid the confusion, we are writing now RF, feedback resistance, is equal to I1. What will be the I1, girls? I1 will be 0 minus V1 over R1 plus 0 minus V2 over R2. Any confusion or clear?
No, it's clear.
Clear. So here now, guys, I will do one more thing. I will simplify this one. V out is equal to, I am going to write RF here now, and we also take minus common. When I take minus common, so it will be written as V1 over R1 plus V2 over R2. Now check it and tell me, is there any confusion or clear?
No, clear.
All right. Now, girls, if I put a condition, if I say R1 is equal to R2 is equal to R, yani both are same. Okay. So can I write V out is equal to minus RF over R V1 plus V2?
Yes.
Yes. Now, so here, girls, still we have some gain. We want to add the amplifier. We don't want the gain here. We want to just add the signals. Yani these 2 signals I want to add. So is it possible? Can I make this factor is equal to 1, which we call unity gain? Unity gain, yani gain is 1. How it is possible? If I put what? RF is equal to R. Yani all resistance are of same to minus V1 plus V2. Did you get the point?
Yes.
Yani, the situation when all the resistances are equal, I will be getting V out is equal to minus V. Minus is there because of I am applying the signal to the inverting amplifier, but I am getting the sum, which is V1 plus V2. Clear? All right. So this is my design. How I'm designing. So I'm designing in a way I just put all the resistance values same. 3 ohm, 3 ohm, 3 ohm. So they will cancel out each other and I will be getting the sum of two signals. So this is like it is working as a adder. It can add signals. Now, it is not limited to add two signals, girls. We can have multiple signals here. Yani, we can have more than two inputs, which I want to add. So here is the next slide, which is telling you the concept, which I just explained to you, girls. And it is saying, here is explaining the same concept which I already explained to you. Now, this is what we said. Yani we can add n number of inputs. For that, configuration will be like that. And if I say all the resistance are of same value, so I will be getting V is equal to minus sign V1 plus V2 plus V3 to Vn. This is called summer. Clear? Clear? Okay. Now, see one question to understand this one. So here is a question. Determine the output of the voltage here, output voltage. So guys, again, we need to find this one. Okay. Do you remember the formula? First of all, when you look the resistances value, you will understand that I need to use simplified version of summer, which is V out is equal to minus in the bracket V1 plus V2 plus V3 and so on. But put the minus sign, put the what you are connecting. I am connecting 3 volt. Okay. I am connecting minus 1, connect minus 1. Connect plus 8, connect split. So minus 10 is the sum. So we have to find the sum. So it's free to solve the question. And it's very interesting also. So inshallah, you will be having lab based on that and you will learn more about the summer in the lab. Okay. So this is one application. Now we will move to the one differentiator. All right. Here is a differentiator, girls. So in differentiator, what is the change? Rather than having input resistance, we used to have here what? Capacitor. Okay. And hope you remember, you are familiar with the equation. Q is equal to C into V. Am I right? Charge is equal to capacitance multiplied by this one, right? Now take yeah. So if I take differentiation both side, girls, like dq over dt, which is here getting what? C dV over dt because C is the constant. So girls, do you know that one? Rate of change of charges with respect to time is called the current. It is equal to I, which is, flowing in the capacitor. So here now, if I ask you, this is the current which is gonna be, pass here like that. So I can say V out is equal to I into R. So I is already calculated. So I can say, what I will say, a negative sign will also be there because it's inverting an amplifier. So I can say RC dV I, any input voltage over dt. So this is the equation for the output for the given differentiator. V out is equal to RC. And girls, what is the RC here? Can you tell me what is this RC here?
It's the time constant.
No. I don't want any gain. Here we are talking about the gain. So RC value will give you gain here actually. Okay. And dV over dt will give you differentiation of the input signal. Now, you will not understand with that, values. You will understand with the signals. For example, girls, okay, you have a triangular function x cube. Okay. And I ask you, girls, differentiate that one. What value you will be getting when you differentiate x cube?
3x squared over.
Okay, 3x squared. Okay, so now look here, it's interesting. So here I am applying a triangular function, triangle, and what I am getting? Square function. So I will apply here triangular function, triangular wave, and I will be getting here a square wave. Do you want to see this? See now.
Yeah.
Yeah. Okay. Go there. Op-amps. Where is the differentiator? Differentiator. Inverting. So this is the differentiator, guys. So here, which form I am applying? Look here. Is this triangular? 5 volt.
Yes.
Now see. So input is here. This one is the input, triangular function. Can you check the output also? What is that one? This is square wave or not?
Yes, it is.
Triangular wave input, square wave output. Easy, interesting.
Yes, really interesting.
Also, you can check the gain is there. We apply 5 volts, we are getting almost 8. So how we are getting? This is because of the RC. There is a multiplication of RC. Yani C and R, you need to multiply them. When you multiply them, you will get some gain also for them. So this is the gain of that one also. So this is called differentiator. Also, girls, integrator. So easy. I will just finish it right now, right here. If I give you x square, girls, and I ask you perform the integration, what you will be getting as output? No, Fai. I am asking integration. Integration.
X squared over 3. Cubed over 3.
Yes, cube over 3. Yani integration. If I have a square signal, if I square wave, so what I will be getting? Triangular wave. Triangular wave, right? So I am going to now show you the integrator. And you know what is the difference between integrator and this differentiator? One change only. Yani I need to replace this capacitor by this resistance. Interchange that. Okay, I am going to interchange here. So I will bring it out. I will connect this one here. As I said, I need to just interchange these resistance and capacitance. So this is the resistance here connected. Now it's become girls integrator. Okay, so I will make input now. What I should give to check this one is square wave. And girls, when I am applying a square wave, I will be getting a triangular wave. So you can see here, I am going to start the simulation. You will check yourself. Clear?
Yes, clear.
And can you see one thing here? The gain is compared to that one is less. Yeah, Nadi I'll give you, but it's finished. It's the last. So inshallah, I'm going to give you break now. Just to make 2-3 minutes. Clear, guys? Okay, why it is there? Because for the integrator, the equation, output equation is like this. V out is equal to minus 1 over RC integration what? V in dt. This is the equation. So can you check the gain, girls, here? AV is 1 over RC. So if RC is more, gain will be less. Did you get the point?
Yes.
Okay, this is the equation actually. Okay, so that's why you can see it is 2 volts, though I am applying 5 volts. This is the reason. Okay, this is the integrator. All right, so let's see to the PPT and we just finish this one. So this is a differentiator, girls, which I already explained to you. What you need to remember here, you need to remember the equation first. You need to memorize this one. We can ask you which type of circuit is this. You should be able to understand that one. Because this chapter is having only 13 slides, which is this is the last one, integrator, which is I already explained to you. And please see this one, what I just explained to you. Just a minute. This one, integrator equation and this circuit. Easy? Clear?
Yes,
Okay, so this is we done with this chapter, guys. Now have a break, and we will start after the break. Okay, it is 3:50. We'll start